Right. So, yes, so good morning, everyone. Welcome to our coffee morning today. We have a very interesting conversation today. One of the last PPI meetings we had at the hospital actually looked into this project. And that was 18 months ago. Fortunately, 18 months later, this project actually got funding from the NIHR. And it's about a new kind of sensor that's very cheap, economical, easily produced, that can hopefully monitor patients' vital signs. So without further ado, I'd like to present our two speakers, Professor Neil White of the University of Southampton and Mark Lamond, who is the PPI representative on the project. So gentlemen, the floor is yours. Neil, feel free to share your screen if you want to.
Okay, so I've got a little presentation that I'll show you. I don't want to do too much over PowerPointing, but there's perhaps just some interesting slides there. So I'm Neil White from Southampton, and Mark, do you just want to introduce yourself before I get started with the presentation?
Yeah. Morning, everyone. I'm the layperson on the project for this, working with Neil. I'm pleased that it's all got funded, and so I sit in on the meetings, and it is a very interesting and worthwhile project.
Okay, so just before I share my screen, it's basically, I can't see myself here. Can you see that? Is that viewable?
Yes.
It is. Thank you, Eric. So this device here is what I'm going to talk about. It's a sensor that's actually fabricated onto a textile. So you can see it's got some flexibility. There we go. I can see myself there. So it's not particularly thick. It's something that could quite easily be mounted on the chest. The current version of it looks a little bit different, a bit like an Oreo, I think. Kind of biscuit. It's a little bit thicker, but this has got all the electronics on it. And what we're trying to do is to make the whole thing smaller and flexible, so it doesn't look too dissimilar from that as a kind of final device. So we're not there yet, but hopefully the project will get us a long way in that direction, so that we have something that's a device that's been registered with MHRA, so we can use it in hospital settings and so on. So that's the kind of aim of the project. Right, here we go. Let's try to share my screen, which is always, there we go. Fantastic. Okay, so apparently I haven't given permission to share. Oh, but we have a backup plan, Mike, don't we? Did you get my?
Yes, I do have your PDF. Let me just share my screen then.
Thank you.
Can everybody see this?
Yep, looks like we're getting some thumbs up.
Okay, great.
Okay, so this project, as Mike and Mark said, has just been funded. It started in September by the NIHR. It's a project that involves Southampton, Nottingham Trent University, who are actually doing a lot of the work on the printed sensors. A company called Zelenic, which is based near Salisbury, and those guys are going to be advising us on getting the paperwork for device registration and things like that. We're partnering obviously with the hospital as well. Our lead clinical advisor is Harry Ackerman, who's a consultant anaesthetist, and hence knows a lot about breathing. But we do also have some kind of secondary partnerships with various respiratory people at the hospital as well. So we've got quite a large pool of people, including, of course, Mark. Mark can perhaps say something afterwards when I've finished, if he wishes to. But it's important, and I think the NIHR are very keen on involving PPI activity at a very early stage. And it will be particularly helpful to us because there'll be an opportunity to feed into the design process, which is excellent. So again, we did start this activity a while ago, but being here today is going to be clearly very helpful as that, and it is an ongoing activity as part of the project. So slightly long title. I'm not a fan of long titles, but I was advised that this was suitable, and quite clearly it worked, so we stuck with it. But it's a new type of respiration device that is a wearable system. And one of the features is that it would potentially allow early detection of respiratory distress. So we can detect when people start to breathe heavily, which can be an indicator for some conditions. So can I have the next slide, please, Mike? So for example, that's fine. Yeah, I think that's okay. So this is a plot from a paper that actually showed a few more vital signs, but the two interesting ones that we're showing here are, so the left-hand side is basically a percentage or a number for things like respiration rate, and the time axis along the horizontal axis covers something in excess of 12 hours. So you can see, for example, this would be a patient that has started to go septic, which obviously is potentially fatal. So towards the end of the plot there, you'll see that the respiratory rate drops to 0 because the patient is very, very unwell. So the interesting factor here is if by measuring SpO2, dissolved oxygen, that actually remains fairly flat through that 12 up to 24-hour period. There's a very small decrease, a few percent. Whereas the respiration rate starts off at, in this case, of about 10, and it slowly creeps up to about 50. So an RR, respiration rate of 50, is very, very dangerous. So basically, by detecting the early onset of that increase, the advantage is that patients can then be treated earlier, perhaps with things like antibiotics. It might be something simple as that, or they could be admitted to an intensive care ward. So that's the whole purpose of this project, is that we can monitor respiration rate continuously. So I'm sure, as you know, when you're admitted as an inpatient and your vital signs are monitored, the only one that's not measured electronically is respiration rate. So that relies on a nurse manually counting chest movements over a period of 30 seconds to 1 minute. And that's done every 4 to 6 hours. So clinically, they're only getting a snapshot every few hours of what the respiration rate is. Whereas, as this graph shows, if you can monitor that continually, then trends can be spotted, and then that can lead to further treatment or further observations for the patients, and hopefully potentially help to save lives. Thanks, Mark. Can I have the next one, please? So this looks like a silly question, but it's actually quite a challenging question for us. And that is, what is a breath? What does it mean? So there's a number of ways of measuring respiration. Our technique effectively does the same thing as the nurse. It counts chest movements. And then what we've discovered is that even with so-called gold standard clinical equipment, there are questions about what does respiration rate mean in terms of breaths per minute. So for example, what this is showing is a signal whereby the first 30 seconds are slow breathing, if you like, and the final 30 seconds are faster breathing. So in the first half of the plot there, we've got 4 breaths in 30 seconds, and that would equate to 8 breaths per minute. And the final 30 seconds, we've got 8 breaths counted over 30 seconds. So that's 16, it's double. So at one point, if we're measuring over 30 seconds, we've got a reading of 8. If we measured the final 30 seconds, we've got 16. And if we average out, we've got 12. So what's the right answer? They're all right. They're all correct, given that. So which one would you use? So logically, I think what we would say is, okay, let's average out over a minute. You know, the parameter that we're measuring is breaths per minute. Why not say, let's do it over 1 minute? So that the answer of 12 is sensible, but technically the other 2 are correct. And this is important for us because, of course, we can choose to measure at any of those points along that graph. So one of the things we found is that we do get sometimes different answers from our device when we compare it to medical equipment. And the reason for that is it's nothing to do with the accuracy of measuring the respiration pattern. It's actually to do with the algorithm that they use to compute the breaths per minute number. And sometimes that's a trade secret and we don't know exactly how to do it. Thanks, Mark. Can I have the next slide? So this is the device that I've just shown you. It was actually, believe it or not, invented by NASA. And they were using it on their rover vehicles on Mars to detect boulders so that the rovers didn't crash into unwanted objects. It's what's called a proximity sensor. It detects objects in its way. So it was invented about 30 years ago, but not for respiration. So we basically discovered it by accident. A number of projects that I ran at the university going back a decade, we discovered that if you make one of these things and stick it on your chest, you can actually use it to detect respiration. So for many years, that device sat in my drawer doing nothing. It had made some good group design projects that Eric will be aware of. You know, the students did very well and we kind of proved it in inverted commas, but I wasn't really aware of the medical significance until I started conversations with Harry a few years ago. And he highlighted some of the things that I've mentioned to you about the importance of continuous respiration measurement. Thanks, Mark. Next slide. So again, I won't say too much about this, but obviously, as you're aware, there is a national early warning score, a news score, where the vital signs are measured and the clinicians look at the numbers that are associated with each of those parameters. So respiration rate is obviously in there. That's the one that's counted manually. Everything else, oxygen sats, temperature, blood pressure, heart rate, etc., is all done by machines. And so those numbers are put into a table, and then on admission to hospital, the clinicians can have a quick look at the chart, the news chart, and basically make a very quick decision about how ill a patient is. So you can see that a score of 0 is kind of normal, and as the numbers start to diverge left and right, it takes you through the green areas into the amber and red areas, which can indicate you know, that the patient's been very unwell. Next slide, please, Mark. So the device itself, we can either operate it as a standalone device, or we could potentially integrate it into a garment like a t-shirt or a vest. And this may have some advantages for certain types of patient that might not want to, or perhaps are not capable of actually having it mounted directly onto their body. We could give them a vest and potentially, for example, let them do monitoring at home, where they don't have to worry about continually mounting the device on themselves. It's already integrated onto the garment, and we just say, wear this vest for 48 hours or whatever. And we do the monitoring while they're in a home environment. So again, this is the kind of vision for the project. We're not there yet, but it's the point that we're aiming to get to. Next slide, please, Mark. I don't want to bore you with the technical details, but just to say that that device, this device, although it looks as if it's just a very thin layer, it actually comprises multiple layers of different materials. So it's a big sandwich of different materials. And for any of you with a technical background, it's called a capaciflector. It relies on measuring changes in capacitance. And it's actually very clever. So NASA did the clever bit by adding an extra electrode called a reflector electrode. And what that does is it pushes the electric field out of the plane of the capacitor into what comes before it. And it's detected what is labeled there as an object is in fact the human chest. So any small variations in the distance between the object and the sensor causes us to get a change in capacitance, which we can relate to a breathing cycle, a chest movement in and out. Thanks, Mark. Next one, please. So about, I suppose it's 2 years ago now, we did some evaluation at the hospital as a proper registered clinical trial. And in the photograph, you can see this guy's actually one of the doctors. He's not a patient. He was happy for us to use the photo. So I didn't blank out his eyes. He's happy for us to use this. But here you can see somebody undergoing cardiopulmonary exercise training. So this is where patients are evaluated before they have an operation. So generally speaking, these patients tend to be elderly and tend to be potentially slightly unfit. And so they're evaluated by putting them on an exercise bike, and all their vital signs are monitored, including respiration. And it's the face mask that this chap's wearing that's actually measuring respiration, clearly very uncomfortable and couldn't be worn for a long period. So typically in the lab, this test is done over maybe half an hour, 40 minutes, something like that. And you can see there's a variety of sensors on the patients, an array of 10 ECG sensors. And the big blue capaciflectors are shown on the diagram. And one of the things we were aiming to do is to look at the optimum positioning for these devices. And as it turns out, we can measure respiration pretty much anywhere on the chest area. It's not sensitive to where we deposit them. And we don't need an array. We can actually get a measurement from a single device, unlike ECG, which requires an array of electrodes. And then the plot, this is what's called a Bland-Altman plot. You might not be aware of this, but it's kind of used as a way of demonstrating your device conforms to a standard. So you basically plot the mean and difference between your device and the gold standard, which in our case is the blue face mask using a technique called capnography. And we can see that what we'd like, so all the data points there, what we would like is to have the blue line as close to zero as possible, so there's no bias. So in other words, our results are reading the same value. And the upper and lower dotted lines are basically the standard deviation, or 2 standard deviations approximately from the midpoint. So we'd like to see those dots being as tightly focused as possible. So in this case, we've got a standard deviation of approximately plus or minus 2 breaths per minute, which conforms to many of the medical measurements that are out there. So it's these results from our point of view are very promising. Thanks, Mike. Next one. Again, without going into too much technical detail, but the signals that we get are, as you can see here, quite noisy. They're all over the place. They don't look like that nice respiration pattern that I showed you. And some of the challenges that we've got is to convert this horrible squiggly waveforms into something that looks more like a continuous kind of sine wave, nice smooth waveform. So we're having to look at different types of clever filtering and signal processing, just as they do with ECG or ultrasound signals, and apply those to our raw signal in order to get a trustworthy waveform that we can use to measure respiration. So again, part of this project over the next 3 years will be to develop suitable techniques to do that. We've got some in mind already that work, and we're hoping to improve on that as we go forward. Thanks, Mike. Next one. I think next one's the last one. So yeah, I mean, this is actually a slide that I presented directly to the NIHR about this project. So we're in a position where we've kind of confirmed that there is a clinical need to do this. And even anecdotally, when I talk to people at the hospital, including the nurses, you know, I was in a meeting with a nurse a couple of weeks ago, and you know, the fact that she could potentially measure respiration rate continuously without observing a patient, as you can appreciate, when a nurse actually measures that, having to stand in front of you, they actually try and do it behind, so you're not in their line of sight. The fact that the nurse is there looking at you can affect your respiration rate. You can become nervous and so on. So having something that's potentially hidden and can do it continuously is quite clearly quite a big advantage. PPI input is essential to this project, as I mentioned before. So we will need to get the device registered. So because we did that early clinical study, it was classed as what is technically known as a research study. The fact that we've done it once, we can't do it again. So what we have to do now is get this device approved via the MHRA so that we can use it again in a hospital setting. So one of the early stages of the project will be to get the device registered to allow us to do clinical measurements. In parallel with that, we will be doing testing at the university on ourselves, on students and on other volunteers. So we'll go through our own ethical approval process within our own faculty to do that. And that will allow us to get quicker results than being totally dependent on doing everything through the hospital. In terms of the IPR is an interesting question because, so NASA have the patent on this, but it actually elapsed a few years ago, so there's no worries about that. The fact that I'm an academic and have published this work doesn't help our case with regard to patenting. So at the moment, in its current form, we can't patent it, but quite clearly as we move forward, there'll be some hopefully clever technical additions that we can make to the technology and patent that, or get the IPR sorted out and start to identify routes to market. Again, that's part of this Invention for Innovation, I4I project. Developing prototypes, well, we have some prototypes already, but we're hoping to be in a position where we can actually, when we do our PPI sessions, hopefully in person, we'll be able to hand them out and let people actually play around with them basically in their own time. It's also been noted by some people that I've been speaking to that there are potentially many other uses for the technology. Sports has been identified, potentially sleep apnea. Somebody could wear this and be monitored overnight, and we could detect the lack of respiration patterns. Home use is, I think, probably going to be one of the bigger markets for this, the fact that you can actually wear it at home. And because it's small, lightweight, and is integrated onto the clothing, you could go down the shops, you could, go out for a walk in the park, and this will continue to monitor your respiration. And quite clearly, if you were at home, either recuperating or being monitored, as soon as you start to do exercise, you would expect the respiration rate to increase. So, a patient in the hospital with a respiration rate of 30 breaths per minute would be of a concern. A patient at home or out in the park having a walk with a respiration rate of 30 is not a concern. And we could detect that case because one of the things that we hope to integrate onto the device are devices called accelerometers that can help us measure movement and motion of the patient as well. So we can actually see whether that patient is moving around or whether they are actually laying in bed. And in fact, which way up they are as well. We can get all that sort of information. So from our point of view, it's very exciting. It's we certainly know that there are clinical advantages to the technology. And for us as engineers, so I've obviously not got a clinical background. I'm an engineer. There's some very interesting challenges for us, and also from a technical point of view, the challenge of actually getting it into a form that patients would be prepared to use it, and clinicians would be prepared to accept the quality of the data that we give them. And it's in a simplistic form as well. We don't want to reach the amount of data that we're presenting. That's something we're very conscious of. But at the moment, we're looking at, as you saw from those signals, very, very detailed, complex forms of data that are of no interest to anybody other than us directly. So when we actually present the numbers, it'll be a very simple system that says your respiration rate is 15 breaths per minute, and we'll monitor the trend over, say, at 1 minute intervals over a number of days, or potentially even weeks, once we get the things like the power consumption down. So that's the kind of that's the project in a nutshell. Happy to take questions, but I'm also conscious that Mark might wish to say something, so I'll hand over to Mark.
Yeah, thanks, Neil, for an excellent presentation. It's very clear, and I think we'll all agree that it was very good. When I went to the first presentation, what struck me was the benefits of this, the way it's currently done, particularly when you may be on an acute ward or general ward, perhaps not so much in ICU. You can immediately understand the benefits of it from the patient point of view. The way it's currently done, I think, I don't know how long it's been done, currently the way it has is probably over 100 years. And in this day and age, it just makes so much sense to move this forward to an electronic measuring device. And then further still, I think as patient involvement, we can bring forward and talk about the home benefits and the external monitoring. So yeah, thanks, Neil. It's very clear and very good presentation. Certainly the benefits are very clear to me, and I think they are to everyone else.
Thank you, Mark and Neil. I'm going to stop the recording now.